Hey everyone, last section, 10.4, woohoo! This is on the F distribution and what's called ANOVA. So this is your final distribution. Um, there's some information about the distribution, some details about it. You use it to find the critical values. So I'm going to jump right into that. Notice the shape changes depending on degrees of freedom. And this one actually has 2 degrees of freedom, where it specifies DFN and DFD. And then we're only worried about right-tailed tests or maybe two-tailed tests. So let's practice with finding those. You'll use the table. To access the table, go to modules, I put it there, or it's in the textbook, and I'll bring it up here right now as well. But we're gonna try this problem, the right-tailed test, and then you have 3 pieces of information there, and we'll just look it up at the table. Let me bring it up. So here's the F distribution. Pages typically come up as this landscape. You can rotate them around if you want, like I've done this one. But the thing about this table is there's a page for each level of significance. Right? So you'll see it right at the top of the page. That one's 0.005. This one's 0.01. Here's 0.025. Here's 0.05. I've already rotated it, so it's a little easier to see. So if you have it printed out, it might be easier, or you can just look at it on your screen. But once you find the right page, it's pretty straightforward. You're just going a DFN 9 and DFD over here 6, and then just find that number. So it looks like a 4.10. So that's been an F value, and since it's a critical value, you're just going to call that a F sub 0. Okay, that's it. Pretty straightforward. Now, if it's a two-tailed test like this other problem, you have one thing to do first. So since the alpha is 0.01, you just divide that by 2 first, 0.005, and look that up. So go to find the 0.005 page. Here it is, DFN9, DFD8. I'm seeing a 7.34. So your F sub 0 would be 7.34. Okay, so you have that technique now. That's the first step. And then you're going to apply this when you do the ANOVA hypothesis testing. Okay, so there's finding critical values. Let's jump right into ANOVA. ANOVA stands for Analysis of Variance. And really what you're using it for is to compare the means of 3 or more populations. So we've compared means of 2 populations, but this one, it's a technique used to compare means of 3 or more populations. Okay, there's a lot that goes into these calculations of the standardized test statistics. And to get a little more background on that, you could look in the textbook or watch some of the videos in my lab. But anybody who really does this test, and it's a pretty common hypothesis test, uses technology just because it's so crazy by hand. So our focus for these is purely StatCrunch, which is good news. These won't be too long. Okay, well, let's look at an example, and we'll take it step by step. So a medical researcher wants to determine whether there's a difference in the mean length of time it takes 3 types of pain relievers to provide relief. Okay, so we have some raw data here, and we have the 3 types of medications, and those are times and minutes, right, of the medications. So the results are shown. Can you conclude that the mean times are different? Okay, so let's set this up. When you set up your H sub zeros and H sub A's, the H sub 0 is always something like this. The means are equal, basically. You can write that out in words. All population means are equal, or just say mu1 equals mu2 equals mu3 equals however many you have. Right? So on this one, we would just have 3. And then HA is just that at least one of the means is different from the others, or just HO is not true. Okay. So can we conclude that claim? That's going to be our claim. Can we support that claim that the mean times are different, or at least one of them is different from the others? ANOVA is always a right-tailed test, so that makes finding critical values pretty easy. Just use that table. Conditions are just some standard stuff, independent samples, random, etc. Populations have the same variance. Okay, so getting to the meat of the problem, finding that standardized test statistic and either the critical value or the p-value, we'll do both. That's when you're going to jump to StatCrunch or the table. So I'm going to jump to my desktop and we're going to do the StatCrunch method and then also get those critical values. Okay, so let's share the desktop here and I can go to StatCrunch. So I have the data loaded in there already. Then this data is in your groups folder if you want to access it. If we go to stat, you'll see ANOVA right there. And this we're doing what's called one-way ANOVA. Right? You're not going to do any of those others. So we're just doing one way. Okay. What do? You select the column. So we're going to select all the columns. I'm holding down my control key or command key actually. Highlight them all. Right. So again, I want click one, and like on a Mac, I'm on a Mac. I hold down command, right? Or it's if you can see it there on what to do. But may highlight all of them. Okay, and then that's all you gotta do. And then click compute. And it'll give you a bunch of stuff. And what do we want here? I mean, of all these things, really what I want is my f-stat. I mean, that's the standardized test statistic. So that's what I'm gonna write down on my handout. F is 1.50. I also get a p-value. So I can write that down below where it's asking for a p-value, 0.269. Okay. And then we're going to interpret what that means in the context of this problem. Okay, what if it asks for critical values? That's when I would jump to my table. Now we have an alpha for this problem. Stated in the problem was 0.01. Right. So I'd find that page, 0.01, there it is. I'm gonna rotate it. There we go. Okay, and then what are these degrees of freedom? So df sub n is specified as k minus 1, where k is the number of samples, or how many categories, or how many medicines in this case, which would be 3. So k is 3, 3 minus 1 is 2. So my dfn is 2. All right. DFD is n minus k, capital N. Capital N is the sum of the sample sizes, total number of patients in this case. So if I add all of that up, I've got 4 in Med 1, 5, and then 4. What's that, 13? Okay, so my capital N would be 13, and my K is 3. 13 minus 3 is 10. Sorry, my dog's barking. Okay. Use those values, 2, 10, and that leads you to that 7.56. Okay. That's your critical value. That's your F sub 0. All right. So that's how that works. If I jump back to my handout, I can finish this problem now by making my decision and conclusion. And you can see, with that large p-value, you kind of know what's going to happen, right? That p-value is larger than 0.01, right? So when I go down here to my step 5, I have a fail to reject, right? P-value is larger than alpha. It's a fail to reject, okay? Or the F distribution, I would draw it, right? So this is kind of either or, either do the P or the critical value, but that's 7.56, but my F was only 1.50, so it's nowhere in that shaded region. So that's also fail to reject. Either way, we get fail to reject, okay? HA was the claim, right? And we failed to reject. That leads me to my final answer there. There is insufficient evidence to support the claim. All right, there's ANOVA, okay? So we cannot support the claim that these means are different. All the medications seem reasonably doing the same job. Okay. So we'll try one more. If you want to try that on your own first, hit pause and give it a go and then play, but I'm gonna go ahead and jump right into it. I'm gonna write down my H sub 0 and H sub A. Yeah. H sub 0 is that all of the means are the same. H sub A, at least one is different. At least one mean is different. And so I might just write that out like that. Okay. I would, verify your conditions and then jump right into StatCrunch. So I'm gonna load this into StatCrunch. Again, I put this one in your groups folder if you wanted to try it. It's in there. So there it is. Okay, and then you're just doing stat ANOVA one way. Highlight your columns and click compute. And really what you're after is that F stat of 6.13 and the p-value of 0.0064. So small p-value, I'm thinking we're going to be rejecting H sub 0. I could get critical values if I want, but here I'm just going to go p-value in this one. And then we can finish this one off. Okay, so with that p-value being less than the alpha of 0.01, that's going to be a reject H sub 0. Okay, and if I'm rejecting H sub 0, what was the claim here? Okay, that last sentence. Can you conclude that there is a difference? So that means the claim was HA. Can we conclude that there's a difference? Yes, we can, because we've just rejected that they are the same, so we can support HA, right? So there is sufficient evidence to support the claim that they are different. Here's my chicken scratch. Okay. Check out my completed notes if you want to see that in a nicer way. Otherwise, that's it, everyone. So give me or shoot me emails if you have questions on these. Give them a go, and then start reviewing for that final after this. All right. Hope all is well with you. I'll talk to you later.